I'm one of the program leads for Program 4, and Program 4 is on quality assurance and compliance and how we can utilize cobots in highly regulated industries is kind of the use case that inspired this program. I'm not going to talk a ton about applications for that today, but I am going to talk about cobots in a couple of different areas that sort of led to or lead my research towards this area. So I'll talk about cobots in our National Industry 4.0 Algae Test Lab here at UTS, and I'll talk about cobots in additive manufacturing, which is one of my core areas. And then I'll end the day with a refresher on what Program 4 is and the projects that are associated with it, so that everyone sees the connection back to it. When I think about cobots in highly regulated areas or where quality assurance and compliance are of significant importance, of key importance, of one of the primary things that needs to be considered for the cobot application itself, I think of this image on the right here, which is where we have cobots assisting in medical procedures. So highly regulated area, industry to begin with, and a very critical application for understanding, one, what the robot's doing, two, what the people are doing around the robot and the interaction between them, and being assured of what's going to happen and being able to track what's happening in real time, and then post operation to see if anything came up, is a feature that is enabled by applying cobots and bringing cobots into this space. And that's kind of the area that this program fits in. And so now I'm going to shift gears and talk about cobots in other places and some of the stuff that we're doing with them. But this is kind of in the back of my mind where we're headed for and the application space, the research that we're going to do in Program 4, where it is one place it's quite useful. So I'll talk about cobots in our Industry 4.0 Algae Test Lab, but first we need to understand what this test lab is. So the Algae Test Lab at UTS is part of the Industry 4.0 National series of test labs from a few years ago, and the use case of this is to scale up the production of algae. So algae's got a ton of uses, and we've built this Industry 4.0 enabled manufacturing facility to help study the growth and the expansion of algae at a production scale. And one of the key features for this, one of the things that we included in it, is cobots to assist in the production process. And we chose cobots because this facility is small, but it needs to have a flexible arrangement where people can be in the lab, but people aren't always in the lab, and the robots need to be able to handle that diversity. So algae itself has a ton of uses in terms of producing fuels or plastics or medical medicines or nutraceuticals, so food stuff, or animals or dyes. There's hundreds of thousands of species, and depending on the different species, you can use it for all sorts of things. One of the things we're using it for right now is actually carbon capture. So it's a fantastic medium, which is kind of the purpose of the lab itself. But to make this, in order to study the scale up in the production, we needed to automate a huge number of the processes in growing the algae in the lab itself, just due to limited people, and to demonstrate Industry 4.0 technologies as they occur, and cobots are a key part of that. So the way the lab works is we've got our photobioreactors where the algae is grown here in the middle, the big tank with the purple light and the smaller tank with the green light. There's a harvester on the right hand side. There's a whole bunch of sensors to kind of measure how the plants are growing, and then we have two different cobotic systems to assist with various processes in the lab. We've got one stationary, and that is used on the inlet side of handling all of the chemicals and the nutrients and the cleaning products to set up the system for either a new batch of algae to be grown or to clean up after a batch has been emptied out of the tanks. And so that's what this one here on the left is. And so that interfaces with all of our tanks, as well as this stand here of reagents and nutrients that will be placed there. Now, somehow we need to get these nutrients over here and coordinate that activity. It could be done by a person, but often we don't actually want to bother with having people do this small task, and so we have a mobile robotic system. It happens to be a Kuka Iwa mounted on a mobile base for it, and that robotic system actually will pick up the nutrients from storage over here on shelves, and transport them over here and put them into the holders here for this robot to pick them up and dump them into the appropriate tank as needed. Now that's one task for this mobile cobotic system. The other task for this mobile cobotic system is at the end of the process. So the growth itself is all automated with pumps and valves and lights within the photobioreactors. But at the end of the process, we have to harvest the algae. And so it's in this very dilute mixture of water. It's a lot of water, and we want to reduce that so that we just have the little plants left, or as close to just the plants as possible. So we need to extract them in some way. Our harvesting system, at least this one in particular, uses a polymerization method. So we inject some chemicals into the bath of dilute algae plants, and it condenses the plants and they float up to the top, and then they get scraped off. And so then we reduce the water by sort of extracting the plants from the top surface with this polymerization. And then they get squirted into little cups. And those cups need to be sealed and placed into the freezer. And that is another task for this mobile robot. Conveniently, it's on a base so that we can do these different tasks independently. But also, the lab itself is equipped with motion tracking, so that the robots can and the lab know where the humans are, and so that they know not to impact the humans when they're going about their business. And so this mobile base can reroute itself if needed to go around humans, or if humans are in the way, it gets paused, it gets stalled. And the choice of cobots for this is because all of the duties that they're doing are lightweight, and we have humans in the mix, which means our safety protocols for the lab itself are reduced because we don't have robots with high payloads. They're not going to cause a lot of damage, and they've got all the sensing in it to impact someone lightly and not cause a lot of harm. So here's just an image. I don't have the video with me today, but here's just an image of the robots working together. This is a staged photo because Aaron here would be normally wearing a safety helmet that's got markers so that the cameras can see him. So this is just a staged photo to show it itself. The video version of this has the robots actually placing the containers in and picking them up. I just didn't have that for today, but if you want to see it, it's on our website. So this is, I like this photo, not because it doesn't have all the safety equipment, but because it shows a couple of things. It shows a collaboration among robots themselves. So the robots need to communicate and interact with each other, as well as a human. And those are sort of two scenarios that are going to be encountered in any automation or manufacturing process that has many robots and people working alongside each other. We have both sets of these types of interactions that are possible. Now, having the cobots themselves is fine and dandy, but where kind of the key points of Program 4 fit into the Cobotics Center and are applicable is not the cobots themselves necessarily, but how do we manage the data that we can extract from them and communicate with the manufacturing process, the people, and the robots to ensure that the activities that are being done are traceable for compliance reasons and within some known bound of accuracy. And that's where this IoT infrastructure comes in. So the data infrastructure is a really key part of integrating cobots into any system. And this is, for me, a key area of interest is in this data stream. How do we find the right analytics for the tasks that are being done, and roll up all of that data into the right formats and communicate it back out with sufficient speed so that we can aid manufacturing processes. And this image here is just sort of a layout of our data infrastructure, mostly in the hardware space, but we've got our base equipment at the bottom. We have some edge computing or integration equipment in between, and then we have our database and our analytics that sit up at the top, and those spit out they translate all of that data, collate it, and translate it into something that is human readable, something that people who are monitoring or interacting with the system can understand relative to the task that they want to do. And so this is a key part of integrating any cobotic system into a manufacturing existing process, is thinking through and planning for this data infrastructure. And so that's my bit on algae. And so now I'm going to switch over to cobots and additive manufacturing. And this is a key area of interest for me, so I thought I'd present some work, and hopefully you enjoy it. Or if you have any questions, we can talk about it at some point. So start all my talks in additive manufacturing about why are we interested in additive manufacturing itself, and largely this is because of the high mix of design freedom, high mix of products that we can make, and the high design freedom that we get from applying additive manufacturing as opposed to other manufacturing techniques. And so this ranges from topology optimization to lightweight things, which is critical for transportation, to customizing medical devices, or changing the way that art and entertainment is done and thought of by reducing the number of constraints on the design side to think about how we produce parts for art. Or assembly reduction, which reduces the cost of the life cycle of products and can reduce maintenance challenges. And then down here at the bottom with the car, this is where we start to get into large-scale fabrication. And in large-scale fabrication is where cobots start to play a significant role in additive manufacturing. For smaller parts, it doesn't make sense to have multiple robots working together, but when you get to large scale, it's quite critical to have to parallelize the fabrication so that we can make things at scale. And this is where the collaboration of robots together in producing parts in additive manufacturing has a role to play. Just as a note, if you weren't aware, a lot of people think of additive manufacturing or 3D printing as these little desktop printers. That is not the space we're going to talk about today. We're going to talk about this space more on the right, where we have large format fabrication. And so there's a huge range of fabrication that can be done with additive manufacturing in the construction or automotive, aerospace industries. One particular example I really like is the MX3D bridge in Amsterdam. So this is a solid metal bridge that was welded together. So it's a wire arc additive manufacturing method that was produced with robots. So you can see on the right here, we have a robot system, and we've got a human there for scale. And the robot is actually on a platform next to the bridge, welding the bridge together layer by layer and building the thing out into free space. And so if you think about the challenges of the environment that this is working in, there's the shape is getting larger, and the robot has to reorient itself to the environment, which is a key task for collaborative robots or robots in general when they're out in the environment. But also, we've got one robot making this bridge. We could make it a lot faster if we had multiple robots working together to make this. And so I'm going to talk about a little bit about the limitations, what's held up that from happening, and how we get around that. So the data process for additive manufacturing as itself has a number of stages. So when we're preparing and producing something through additive manufacturing, we start off with the design. So I'm going to pretend the design is done, and I'm going to focus on some of these other areas. So we have some design that we'd like to make. We have the geometry of the shape that we want to produce. That goes through a couple of file conversions, and then it gets converted into a plan for whatever the additive manufacturing process is that's depositing it. It gets converted into a plan to lay down the individual elements of material to build that part. And so that's where this toolpath planning comes in. And it is in this area that we have some limitations that are just inherent to the way that it's been done thus far that make it difficult to collaborate and enforce some limits on our fabrication process. And that's where I'm going to focus today. After we have the toolpath plan, we send that to the fabrication system itself. It deposits the material, hopefully according to the plan, as close as possible, with minimal errors or no errors. And then we extract the part, and then there's some post-processing that has to be done to clean up the surface or add, tapped features or high precision areas need to be post-machined. So that's generally how additive manufacturing works. But let's tune into this toolpath planning section itself. So the way toolpath planning typically works in 3D printing is you start with your STL file or whatever 3D format you've got that's tessellated triangles, and you put a series of planes through it. So every increment in layer thickness, you put a plane through that, and the intersection of two planes is a line, which is convenient because computationally it's very efficient to compute the intersection of two planes and get a bunch of lines. So at every layer, you get a bunch of lines, and then you string those lines together into line segments. And then you order the line segments to be deposited by the material or by the machine itself. And so the way that this is done is we're slicing in layers. So we have a bunch of single layers, and most 3D printers or most software will then they'll deposit one layer, and then they'll go to the next layer and deposit that whole layer. And once that whole layer is finished, then they'll go to the next layer and deposit that whole layer. This is convenient because it assures that you reach all of the spaces in the model and can deposit the whole thing. But it sacrifices some speed by including a lot of wasted motion jumping around each layer just to deposit that layer. But it does save on the algorithm side for having to think about how you're depositing the material. It also reduces the deposition itself within each layer to a single instance of the traveling salesperson problem, which computationally there's a whole bunch of techniques to try and solve that. But yeah, so it's a single instance, which most machines just start at one side and move their way across to produce the whole thing. So very sort of simple algorithm to solve that traveling salesperson problem. I see this as an issue because each layer is evaluated in isolation, and the fill pattern is simple. So what we're doing is we're giving up kind of early in how we plan our fabrication before we even get to looking at the model as a whole. We're just looking at 2D slices, and I think there's an opportunity to change that. And so we've been looking at this for a few years now to change how we think about planning for additive manufacturing as a whole. And so if we look on the left, this is a standard toolpath plan for this object. So this is a sponge holder. And on the left, we can see that every layer is deposited in isolation, and the red lines between all of the poles are wasted motion. That is motion in which the deposition head is not extruding material. And so from a manufacturing standpoint, that is a waste. It's non-productive time, it's non-productive motion, where the robot is moving, or the extrusion head is moving, and nothing of value is happening. We tried a simple heuristic algorithm to try and reduce that by not constraining ourselves to individual 2D slices of the model, but allowing the dependency, so the geometric dependency of the model itself, to inform where we can deposit. So by that, I mean, if I'm depositing one pole, so long as I don't restrict the access to any other pole, I can continue depositing that pole as long as I want without hopping to some other place. And so that is the key change that we've made in the structure of how we plan for this. So if I have a very long, thin extruding head, I could deposit this entire pole before moving on to any other pole, because I'd still be able to reach the rest of the poles. And so that's kind of the key idea, is to relieve this constraint, that is to do an entire layer before moving to the next one, and actually inform the reachability of the extrusion head to the geometry that is induced by the interaction of the part and the extruding head itself. So part of the reason that we have to hop around a bit in here is because the extrude that we use to produce this actually has geometric constraints, and if we go too far in any single pole, it will collide with one of these other poles. And so at that point where the extruding head would collide with one of these other poles, we hop somewhere else. So here's one heuristic. And then we thought about this heuristic a bit more and tried a different rollout strategy. So in this case, we're using Monte Carlo tree search. So we structure the entire model as a dependency tree based on this geometric and reachability limit. And then we cluster groups of line segments across layers into little clusters, and we then randomly search for the best overall path to produce this entire part. And so those are the two heuristics we're using there. So this is where we started. This is all with a single extruder head. And the next, so there's a cobot talk. So the next logical step is, well, what if I had multiple printers working or multiple heads, multiple extruding heads working on this problem simultaneously? Could I further reduce the wasted motion and accelerate our fabrication time? And so that's where we've gone to next, is where we have robots working together. So we've got, in this case, hardware and software, two collaborative robots working in the same space and dividing up the fabrication of the entire geometry among each other. And so this is where you need some special collaborative mathematical tools. In this case, we use decentralized Monte Carlo tree search, where the robots are predicting ahead a few steps and then sending information back and forth to each other as to what their plan is and what the other one is doing to ensure that they're not going to collide. And so what are the results of this? Well, for clarity, we had one robot print pink and the other robot print black. And so you can see we started with our models here. And then the robots would actually transition. So one robot printed all of the black and the other robot printed all of the pink of these two models. There were multiple models being printed simultaneously, which is why there's more black than pink in the ones that we're showing here. But the black and pink show very clearly that the robots are switching between the different parts to optimize the fabrication of the whole set of parts that need to be produced at one time. Now, there's a simple way to split up fabrication, and that is to divide the area that is being printed into segments and just say, okay, robot 1, you take this half, robot 2, you take that half. And if you do that, and you have parts that overlap these sections, you cause conflicts at the boundary and less than optimal allocation of the deposition path itself because of the relative motions that the arms have to do around each other. If you don't restrict that and you allow the robots to actually enter space that is closer to the other arm than to itself, you can increase. So in this case, we're increasing the utilization, which means we're decreasing the overall time. And so the sigma being higher is better. That means we have more robots working simultaneously for a greater portion of the time that is being fabricated. So we have less downtime for both robots, the higher this number is. So if we allow the robots to actually share the full space, we actually get better utilization overall. Now you may see, so someone may point out that in the zone blocking, so that's where we just segment it. In the zone blocking, we have one data point way up here that actually is pretty good. And that is a special case of when we have parts that are far away from each other, and it makes more sense for the robots to just build their own part and not to ever switch. And so that is an instance where zone blocking finds the best solution right out the get-go, and a stochastic search method like Monte Carlo tree search will have to spend some time in order to find that as the optimal path. The next stage of this research is a more sophisticated algorithm for allocating work between the robots and reframing the problem itself into larger clumps of contours so that we can more quickly discover the optimal toolpath for the entire part. And that's where this work has gone to. And the reason I bring this up is because when we start thinking about collaborative spaces and collaborative robots and people in collaborative spaces, the algorithms and the data processing itself play a huge role in the efficiency of the work that's being done. And so this is one application of where taking a different approach. So we're actually doing this deconstruction, this Reeb graph deconstruction on the model, and ignoring all of the toolpath planning that typically happens in the slicing. We're ignoring all of that for our initial optimization of the layout, and that actually generates a better result. So taking a step back and reframing the whole problem with new algorithms has led us to what I think is the end result. I don't think we're going to be able to improve the fabrication of 3D printing for point-based extrusion any further. I think this is as far as it's going to be able to be improved. And so taking a step back and looking at the algorithms for what makes sense for the problem that you're working in and utilizes the features of the collaborative robot itself has really come to a fantastic solution for this. And so we can see here just the image on the left. The hands are the processes that we're going from. So we define some height layers. We discretize the part into some clusters, and we reorder those clusters computationally, and then we expand each cluster into the actual contours and plan within those contours. And then on the right is just an example of the wasted motion in red for the default plan versus what our newest algorithm does, and there's very, very little wasted motion on this topologically optimized bracket on the right. All right, yeah, I think I'm doing good on time. Okay, so we're gonna switch over to program 4. So how does this relate to program 4? Michelle Dunn and I are the co-leads for it, and when we think about collaborative robotics and people, there's some things that people are better at than robots, and some things that robots are better at than people. And the idea of these spaces is to bring them together and utilize those best features. And so, classification, pattern recognition, and dealing with variability are things that humans are great at. Incorporating new information, people can do that quite well. But they can't do the same task forever, the same way with the same consistency as robots can do. And so that's kind of the two areas we're looking to bring together in a collaborative robot space. When we look at highly regulated environments, so if we think about medical or high precision manufacturing or aerospace, things that need lots of inspection, we find further benefits of cobots being in that space that match the tasks and the requirements of the highly regulated environment itself, or the quality assurance. And that is, we need to track a lot of things. People can't keep in their mind simultaneously more than about a dozen different things, and even that's quite impressive for folks that can. I think I can keep about 3 things in my brain at any one time, and that's maxing it out. But if we need to track a high number of things in a regulated environment, so that we can check for surface roughness, check for material properties, check for that processes were being done correctly, check for that paperwork's been filled out correctly, that it's been filled out timely, that all the necessary steps have occurred in the proper order, we have a high number of things to be tracked in lots of regulation or compliance. We also want to verify manufacturing products at many stages. So if we look at one of our partners, Cook Medical, in the graft fabrication stage, they need to inspect many of the knots that are tied, and they need to inspect lots of dimensions, and they do this throughout the process. So we have multiple inspection stages that occur during production, and we want to verify that things are being done correctly at those stages to prevent having to rework stuff later on. So it saves time and money if you can catch errors early on. We also have fairly narrow margins for acceptance. So there's tolerance ranges that need to be met, and these need to be measured fairly accurately. And human measurement can be good, but as people get tired or fatigued or having a bad day, they may make mistakes that robots are not likely to make. There's also a lot of documentation that needs to be done. So we need to record all of these numbers and record them correctly. And then there's also all of these reviews. So if you need to do an audit, you need to pull up data or have people come into the room and observe what's happening. Well, with cobots, we actually get almost all of these things inherently. So by adding the sensors, the sensing of the cobot itself, we get the consistency within the range of accuracy of the sensors. We get precision, we don't get any fatigue, and we can track things continuously. So for auditing purposes, you don't actually need anyone to then stop work and come in and audit things or arrange a special day. You can actually pull up in near real time the activities that are being done and all of the past work that's been done previously that's been recorded continuously. So you have this opportunity to change entirely how we do audits, and you could do them at any time randomly, simply by interrogating the data that's either being recorded live or was recorded recently. We also can, because of this continuous monitoring, we don't have to make necessarily take separate stages to do verification. We can do verification as we produce the part. And this will save a lot of time, and then we can document that automatically, right? So if we're collecting all of this data and we set up the algorithms and the interpretation to match the documentation that needs to be done, we could collect and fill out this documentation as things are being fabricated, so that we waste no time in the documenting itself, and it occurs simultaneously with the production. And so that's kind of the impetus for the program 4 in here. So we have some potential product areas that program 4 may be applicable to, that is medical devices, defense products, civil aviation, or any high precision or highly something that needs to be inspected a lot or has a high documentation load can benefit from the work that we're doing in program 4. And then this is just reframing of things. The cobot can actively participate in all of these processes, right? So it can do these simultaneously with the human, or actually perform them independently of the human. You know, someone needs to go take a break, the robot can continue inspecting things and do its tests while someone is taking a break or overnight. And if we set up the data infrastructure correctly and match that with the documentation requirements, we can automatically fill out and automatically document the things that need to be documented. And this can be good for multiple reasons. One, it could be simply used for internal process improvement, or it could be used for validating or verifying compliance with regulatory requirements. And so what will our program focus on? So we're going to focus on four main things. How do the emergent behaviors between cobots working together, cobots working with people, and people working with cobots, what new tendencies will occur from this new environment that is being created? How can cobots actually monitor their own behaviors to ensure that they're doing things in line with what they should be doing, and they're not going out of spec or going out of calibration? How can we integrate the data and the sensors, use the sensors that are native to the cobot or added sensors to assure that we have that we perform these quality inspection, that these measurements are what we want to measure? And then how do we translate that data into the business processes and the documentation, and identify any trends of going out of conformance along the fabrication process? And so this is split into 4 projects. So here we have preserving compliance during these emergent behaviors, because we don't want to lose our quality production as we have this new behavior. Try and understand how a skilled craft person is going to fabricate something, and bring that into the cobot system itself, so that we can actually make things as well as a skilled craft person and get that input, do that knowledge transfer. Connect to business processes and perform our data analytics to validate what we're doing is, one, verifiable, right? So it's within calibration, and having the cobot do that self-calibration, and 2, meets the requirements that need to be done, and 3, is interpreted into the right format for whatever documentation or human interpretation needs to be done after the product, after the production's been done. And I have slides on each of these projects, but we've presented this before, so I thought I might stop for questions here at this point.
Thank you, Mickey. That was great. It was so fascinating to see the whole picture coming together. So do we have any questions from anyone in the audience? Okay, I have a question in terms of so the MX3D project, the bridge with the sensor. So that's one that we've looked at in the past and a really interesting one. That project you mentioned had sensors in it, right? And the sensors were, I think, monitoring the structural performance of the bridge. And also, I think, collecting data in terms of how many people go over that bridge and stuff like that. Have you put sensors into any of your 3D printing and also tried to collect data about like the performance of the material that you're working with? Or is that sort of beyond the scope of
that? That is definitely something I'm very interested in. I haven't had a need to do that as yet, but some of my colleagues at UTS are doing that with mineral technologies. So we have these spiral separators that are being printed and putting sensors into that to try and identify wear over time. So are you familiar with that project, Glenda? Have you heard of this?
No.
Oh,
No, I'm
okay.
not
All right.
familiar.
Sorry.
Not
So
that particular project, no.
So that's actually another instance of robots working together to produce these multi-meter tall, meter and a half wide slurry separators for mining.
Oh, yes, I am
yeah.
familiar with that project.
So you dump a slurry down this this corkscrew shape, and the centripetal force of that causes the constituents within it to separate. So by the bottom, you've got high value, medium, low value sort of buckets at the bottom. Depending on the composition of the slurry that goes down that, you get different wear rates for the coating on that. And so the goal with embedding sensors into these custom 3D printed spiral separators is to try and identify when that wear is going to happen so that you can produce a new one in time, rather than trying to predict it ahead of time and having a lot of stock sitting around.
Cool. Teresa,
can I follow up on that question? Not with the sensors inside the material, but the sensors outside to detect whether the 3D printed, I mean, it got, I don't know, something wrong and you need to correct for some paths. Have you look into something like that?
I'm hoping you're going to help me do that, Teresa.
I would love to.
Yeah, thus far we've been focused on the algorithm side, like how can we produce things as fast as possible with as little wasted time as possible. And now we started incorporating the material properties that we can actually plan for, residual stress and plan for curing rates. But we haven't gotten to your area yet, which is the visual processing of like how accurate is the print compared to what we intended to do. And so I'm hoping you'll be helping me and Tim work on that.
Yeah, awesome. Thanks, Vicky.
that sounds awesome. Jared, did you have a question? You see movement.
Oh, you saw me reaching for the keyboard. I was wondering with the 3D printing, Mickey, with the latest algorithm you have, is it still assuming a kind of horizontal layer print on each of those different subsections? And have you thought about 3D printing where you might be able to vary the angle of that plane and print sort of off to the side and things like that?
Yeah, no, that's a great question. Yeah, so we have sort of two independent lines of work at the moment, and we need to join them at some point. So we've been doing non-planar printing, just on its own. So non-planar printing, so we can vary that starting from flat and then varying it to non-planar, try and follow stress fields, and then back to flat so that we get the final shape at the end. And then separately from that, we've been working on this algorithm side, which is focused on like, I've been given a shape and I've been told which way it's going to be printed. Optimize that problem. But yeah, I'm hoping at some point we're able to marry the two, and do some really cool stuff.
I have another question that's in terms of the program, and when you talk about the data analytics and, you know, capturing the data, what do you do in terms of, I guess, like visualizing and communicating that data? Do you have some, yeah, I'm just keen to learn more about how you turn that data into something that's easily accessible for like the industry partners, or maybe somebody on the workshop floor.
Yeah, and I think that's, I mean, there's no like single answer, I don't think, for that, right? So part of those projects 3 and 4 related to that are going to be dependent on domain expertise and, you know, the specifics of what, you know, what's being made and what needs to be communicated and how that needs to be communicated. So there's some specifics that need to happen there, and I'm hoping through those projects we can come up with a framework that makes it easier and quicker to develop something that's useful. So kind of like a translation framework, so to speak, of like, here we have a bunch of, you know, raw numbers on a temperature, you know, an infrared temperature sensor. What does that mean? I'm hoping that there's a couple of layers of translation that we can organize some, you know, sort of semantics for what are some standard ways to interpret that into something that is useful for somebody. And then there'll have to be some customization at some point to go, okay, it's useful for understanding, you know, temperature distribution and that this area is hot and this area is cold. But what does that mean for my process? That's going to be domain dependent.
Awesome. All right. Well, we've reached 11 o'clock. The time has flown by. I guess if anybody has any questions or want to follow up directly with Mickey, you can please do that. Highly encouraged to have these conversations offline. And thanks everyone for coming today. It's been great to see you all. And thank you so much, Mickey. Really enjoyed that presentation and learning more about your work and the program. So looking forward to seeing how it all continues to unfold.
Thank you very much. See you all.
See you, everyone.